All right, so now we're going to apply our Poisson distribution. We've got our same data set from above with its mean of 2.75. My relative frequency, well, that's the same as probability. My total number of values was 60. It was 60 people surveyed. So this would be 40 out of 60, 12 out of 60 is 1/5, 15 out of 60 is 1/4, 13 out of 60, 7/60ths, 4 out of 60 is 2/30ths, or 1/15th, of course. That's 1/20th, 1/60th, 0, 1/60th. So now if I apply a Poisson distribution to this, I could calculate each of these, and the fastest way to do that, well, I've got two ways that I can do it. One way is I can go into my y equals and just put in this formula. So my mean was 2.75. So I'll have 2.75, and then I'll raise that to the x power, and then I'll have e raised to the negative 2.75, and my denominator is x factorial. I can find that over here, right? Or I could also go into my distribution, take a Poisson PDF, and put in a mu value of 2.75 and an x value of x. Notice your calculator uses lambda for the mean, formula booklet uses m. Normally we write it with mu, all the same. All right, so now I could go into my table of values and get my different values. I see that they're the same. And what I also see is that they don't match these values. So at 1, I had 0.2, whereas here it's 0.1758. And these are not going to match exactly because this was experimental data and this would be a theoretical outcome. So my values are going to be similar. So here I've got 0.001, down here 0.0004, and we can see as we increase that our values are getting closer and closer to 0. These outcomes are becoming less and less likely, and we know that's true because 17 is really far away from our mean of 2.75.